Okay, so you're writing the negation of the quantified statement. All mathematicians are human. And if you recall, there was like a little crisscross chart that if you write all A are B, some A are B, and then on the right you have no A are B, and some A are not B. And then if you draw your crisscross marks, then those were negations of each other, the arrows to each other. So all are goes to some are not. And so we're going to change this to some mathematicians are not human. And so that's it. And if you had started with some are not, then you would have changed it back to all are, okay, because those are negations of each other. Okay, number 10. It says, let P represent a true statement and Q represent a false statement. And you want to find the truth value of this compound statement. So when you know what P and Q stand for, then you don't have to do an entire truth table. Instead, you're going to substitute these truth values like it was a math problem. And so starting with not P, since P is true, then not P is false. And since since Q is false, not Q is true. Okay, so now we can start from the innermost parentheses and work our way out. So an and is only true when they're both true. Okay, so notice that both sides are not true, so therefore this is false. So all I did was that parentheses right there. So now inside the bracket is an or statement. An or is only false when they're both false, and that's not the case here, so this is true. Okay, so I did what was inside the brackets, but now I need to go out to the negation, and the negation means I want the opposite of what's there. So the opposite of true is false. Okay, for number 12, it says, use De Morgan's law to write an equivalent statement. Two, it is not true that apples and beets are both fruits. Okay, so for some of you guys, it'll help to translate this to a symbolic statement, but not necessarily. It's up to you, okay? But first, we want to identify what key words you see in this statement. It is not true that, and. Okay. So we can say that P stands for apples are fruits. Or you could have said an apple is a fruit. Okay, there's variations to that. And Q would be beets are fruits. Okay, it is not true that will always translate to a negation outside parentheses. And then we have apples are fruits and beets are fruits. So we have P and Q. Now, in the directions it said use De Morgan's law, so that was a hint. That may or may not appear on the test. It's just you're looking for an equivalent statement. And when you see this, then you know you can use De Morgan's law to make an equivalent statement. So we're going to distribute that negation and flip the and. So not P or not Q. And so to write that, we get apples are not fruits or beets are not fruits. Or you could say an apple is not a fruit or a beet is not a fruit. So that's the equivalent statement. We just covered De Morgan's law. And so that was the one that we did for the and, but it also works if you have an or inside of there. Okay, we also know that an or statement can be rewritten as an if-then statement. And so what's the pattern for that? Okay, so you are negating, and it doesn't really matter which one you're negating. Just start with one of them, and that's your if part. So if we start with the P, you could say not P, if not P, then Q. But you could also have started with the Q and said if not Q, then P. And notice these are contrapositives of each other because that's the other equivalent form that we have. If P, then Q is equivalent to its contrapositive. If not Q, then not P. Okay, did I miss any equivalent statements? Okay, and then what's not equivalent to the original if P, then Q is the converse. So what do I do to write the converse? Switch the order. No, don't negate both of them, just switch the order. Okay? Inverse. Negate both sides, but keep the order the same. Okay, so these are not equivalent to the original. And then this is your contrapositive over here that is equivalent. Okay, so it's helpful to remember all of those for that previous question and then also this next one. So for it wants you to write an equivalent statement for the given statement. If I live in Bangkok, then I live in Thailand. Okay, so what keywords do you see in here? If then. And so P is I live in Bangkok. And Q, I live in Thailand. Okay, so this original statement is if P, then Q. So we want to write one that's equivalent to that. And we have a few ways that we can write an equivalent to an if-then. Now, usually the most common one is the contrapositive right here. That's usually what we're looking for. So that means we're going to take if not Q, then not P. So then you can look at your multiple choice to see if that's one of the statements that's available as one of your options. Okay, because that would be if, what? Good. If I do not live in Thailand, then I do not live in Bangkok. Okay, so looking at our multiple choice, that is B. Yeah, that's choice B, so there you're done. Now, if that hadn't have been one of your choices, then you would have to look back at all your other equivalents and say, oh, maybe the if-then goes back to an or statement, and something like that, okay? So number 16, another equivalent question. I ate a cucumber or a candy bar. Okay, so what keyword do you see here? Or. And so P stands for I ate a cucumber. And Q, I ate a candy bar. Good. Way to put it in a complete sentence. So we have P or Q. So looking back at our list of equivalents, notice right here I see P or Q, and I can rewrite that as an if-then. And so I just have to pick one of them to make it my if and negate that one. So I have two options here. I could say if not P, then Q, or I could say if not Q, then P. It could be either one of those options. And so if it's the first one, it's if I did not eat a cucumber, then I ate a candy bar. Or it could have also been if I did not eat a candy bar, then I ate a cucumber. So looking at our choices, okay, D is this one right here, yeah. So if I did not eat a cucumber, then I ate a candy bar. Okay, for number 17, I think I'm going to show that on the screen. And so it says, the table shows ice cream cone sales at an ice cream shop. Let P and Q represent the following statements. P stands for vanilla is the best-selling flavor. Q stands for chocolate chip outsold strawberry by 13,000 cones. And then it shows you the chart for sales at that ice cream parlor right there. Okay, the first thing it wants you to do is write the symbolic statement below in words, and then use the table to determine the truth value of the statement. Here is what we're translating into words right there. So if not Q, then not P. And so looking at what P and Q are, I have to say if chocolate chip did not outsell strawberry by 13,000 cones, oops. Then not P. So then vanilla is not the best-selling flavor. Okay, any questions on translating that into words? All right, so first of all, we can look at our choices and eliminate some of them because now we have the translation. And so this is, we can rule out A, because if, then, and not. Notice that it forgot to negate. It forgot to negate the first part here. Okay, so we can rule out that one. Okay, B, if chocolate chip did not outsell strawberry, then vanilla was. Okay, forgot to negate this side, so that's not an option. If chocolate chip did not outsell strawberry, then vanilla was not the best selling, so that's good. And then D has the same statement. Okay, so either the statement is false or it's true. And so that's what we have to determine now. So what I think is the best way to do this is just focus on P and Q and look at this chart. So first of all, was vanilla the best-selling flavor? Okay, so no, it had 31,000 sales in cones, whereas chocolate had 33. Okay, so that means that P is false. And now Q, chocolate chip outsold strawberry by 13,000 cones. Okay, so what do we have to do with the numbers? Subtract. So 27 minus 14 is 13, and these are in thousands. Okay, so chocolate chip did outsell strawberry by 13,000 cones, so this one is true. And so now we can take a look at our statement. If not Q, then not P. Well, not Q, since Q is true, not Q is false. And since P is false, not P is true. And the only time an if-then statement is false, if true, then false. Good. So this is not that pattern, so therefore this is a true statement. And so that means that we're choosing D as our answer. Okay, so for number 20, they want a truth table. So we'll start with that. And so how many different letters do you see? 2, a P and a Q. And so how many rows are going to be in our table? 4. So we have true, true, false, false. True, false, true, false. Okay, so we need a column for if P then Q. And if P then Q is only false when it's if true, then false. If true, then false. This is the only row that's going to come out false. So all of the other ones are true. And then they did this all in one table to show that they're equivalent. That's what the answer, the answer choices are. So now we have to do columns for this one, but we still need a not P, so let me throw in that column. So this would be false, false, true, true. And then not P or Q means that I'm comparing these two columns here. And an or is only false when they're both false. Okay, so we have true, false, true, true. And so when you compare the two columns from those two statements, notice that those two statements are equivalent. They have the same truth values in those two columns. Okay, so now that you know that these two are equivalent, now it wants us to write an equivalent statement too. If the garden is not watered every day, the flowers wilt. Okay, so what are the key words in here? If not, okay, there's actually no then, but it's assumed there. And so P stands for the garden is watered every day. and Q, the flowers wilt. Okay, so what we currently have is if not P, then Q. And so it wants you to follow this pattern. We have an if-then statement. And notice what's changed here. The if part gets negated. The then part stays the same. Okay, so we want to write the negation of, we want the opposite of not P, in other words, okay, because these are opposites here. So the opposite of not P is P, or we're going to leave the then part the same. So this is how we want to write it, P or Q. So our statement is, the garden is watered every day. Or the flowers wilt. And then they use the word either in front. Either the garden is watered every day or the flowers wilt, which we know is the same thing. You can throw an either in front. And so that is choice C as far as your translation goes. And the table matches as well. All birds have feathers. No mammal has feathers, therefore no mammals are birds. So you need to use an Euler diagram on this to determine whether it's valid or invalid. Now remember, you're not trying to figure out whether the conclusion is true or false. You're trying to figure out whether this is a good argument or not. Okay? And so don't try to make sense of it that way. We start with the first premise. All birds have feathers. And so the key word there is all. Okay, so you need a circle for birds and a circle for feathers. And all means that the birds are inside feathers. Good. The first item has to be inside the second item. Okay, so here's our circle for birds, and here is our circle for feathers. Okay, now the second premise says no mammal has feathers. So the key word there? No. We already have a circle for feathers. We need a circle for mammal. But before we do that, you always want to make sure that if you have more than one possible way to draw this, you're trying to draw it in a way that proves the conclusion false. Okay, so I need a circle for mammals, and I know for sure it cannot touch the feathers. And there's really only one way, to draw this. There's going to be a circle somewhere out here that doesn't touch anything else. So here's my mammals. And it says, therefore, no mammals are birds, which shows that this is valid because the mammals does not touch the birds. And there was no possible way that I could have drawn that to make the bird circle touch the mammal circle, because that's what would have proved it false. And so this is the only way to draw it, so there it's valid. Okay, if there had been a way for me to draw that circle so that it touched the circle for birds, then it would have shown that it was an invalid argument. All right, 27, same type of question. All rock stars are performers. Okay, that looks like an O, but it's a C. Meg is a performer. Therefore, Meg is a rock star. Okay, so in the first premise, the key word is all. And so I need a circle for rock stars and performers. And which one goes where? Okay, good. So rock stars is inside of performers. Okay, Meg is a performer. Notice that's not a quantitative statement. There's no all, some, or none in there. So we're just talking about one item that fits inside of one of these circles. Okay, so we know that Meg is a performer, so somewhere inside of this big circle goes Meg. But we want to see if we can prove the conclusion false. Okay, it's saying Meg is a rock star. Well, if I draw Meg right here, she's still a performer, right? But is she considered a rock star in that spot? No, she's not inside the circle for rock star. So I have just drawn it in a way to prove it false. So that's what shows that this argument is invalid. So again, your goal is to try to make it not work. If you can make it not work, then it's invalid. Okay, number 34. Given that P and Q each represent a simple statement, write the indicated compound statement in its symbolic form. So it's telling us that P stands for, this is a brontosaurus. Oops, brontosaurus. Q stands for, this is a dinosaur. And it says, being a dinosaur is necessary for being a brontosaurus. Okay, so first of all, what are the key words that you see in that sentence? Is necessary for. So what type of statement is this? An if-then. So the question is, for this if-then, is necessary for. Is that one of the ones that keeps it in the same order or reverses the order of the if-then? Reverses. So this is your if and this is your then. But when you write it symbolically, you have to write it if, arrow, then. And so I'm going to start out with what letter? P, because that's what being a brontosaurus is, P. If P, then Q. So there it is written symbolically. So if you need to make a note, page 114 is what reviews all the equivalent ways of if-then in words. Okay, one last question from section 3.7. Number 7. Okay, so you have this argument, if P then Q, if Q then P, therefore P and Q. It says use the truth table to determine whether the symbolic form of the argument is valid or invalid. Now the first thing I could do is check that chart on page 170 to see if this is one of the common valid arguments or common invalid arguments, and it's not. Okay, this doesn't appear on that chart. So I can't use the shortcut and say it's the fallacy of the converse or anything, like that. So in order to do a truth table, the first thing you have to do is write this as one long compound statement. So remember, you take the first premise. Since it has more than one letter, put it in parentheses. And the second premise, and since that has more than one letter, put it in parentheses. Those are all my premises, so I'm going to put that all in brackets. And then I need an arrow leading to my conclusion. Now, since my conclusion has more than one letter, I'm going to put that in parentheses as well. Okay, so there is your argument in one symbolic compound statement. So now, truth table. How many different letters do you see? 2. So you need a P and a Q. And so true, true, false, false, true, false, true, false. And then just start inside one of your parentheses. So if P, then Q. Remember that that is only false if you have if true, then false equals false. So we have true, false, true, true. Now in the opposite direction, if Q, then P. So this time, the Q is the if part, and the P is the then. So we're going in the opposite direction here. If true, then true is true. If false, then true is true. If true, then false is false. And if false, then false is true. Okay, now I'm going to do the and statement between my premises inside of brackets. So that means I'm looking at these two columns, and what do I know about an and? Okay, it's true when they're both true. So in the first row, true, false, false, and then also true in the bottom row. Okay, now I need to do my last parentheses, P and Q. And so I'm looking at my original two columns, and we just stated that an and is only true when they're both true, which is the first row, and then all the rest are false. And now we need to do the if-then between the premises and the conclusion. Okay, so the premises, this and statement is your if, and this is your then. So if true, then true is true. If false, then false, true. If false, then false, true. If true, then false, false. Okay, and so now we look at the last column. Is this valid or invalid? Invalid, because in order for it to be valid, it needs to be all trues. Good.